Hello everybody, and welcome to the fourth and last video in the series. And today I will be talking about vectors and their use in physics. And I will also briefly talk about some tools that you can use to plot graphs in both 2 and 3 dimensions, since visualizing processes can be extremely useful. There are many quantities in physics that have both a magnitude and a direction, so it is convenient to take a look at a very convenient mathematical object that helps us handle all the operations that involve the above-mentioned properties, and these objects are called vectors. When talking about vectors, you have to be very careful, since there are other useful mathematical objects such as lists, arrays, and collections, and some of these objects might share properties with vectors, and operations similar to those possible with vectors can be defined, but they are used more for convenience rather than them being actual vectors. Oftentimes you will encounter these quantities being referred to as vectors, but their terminology might not be very accurate or even adequate. Let's just say that convenient. In this tutorial, I will talk about the properties of vectors in 1, 2, and 3 dimensions, although we are mostly going to focus on vectors in 2-dimensional space, since most of the properties of 2-dimensional vectors can be extended to 3 or more dimensions. The only quantity that is particular to 3-dimensional vectors that will be mentioned in this tutorial is that of the cross product. So well, let's get started. The idea of vectors has been around since even before the first conception of classical physics back in 1666. However, the notion of vectors as the modern mathematical objects has been around for just under 200 years. The modern idea of vectors was first introduced by William Rowan Hamilton when he was working on very complicated mathematical problems that required numbers beyond the real numbers. This is a very long story, but the essential part is that the notion of vector did not quite emerge in the context of classical geometry. It was not until the late 1800s that vectors took the form in which we know them today. In this tutorial, I will introduce the basic notation and operations that can be done with vectors in 1, 2, and 3 dimensions, although most of this can be easily extended to any number of directions. Now, before going into complicated topics, let's take a look at vectors in 1 dimension. So, consider the following problem. A female parrot is standing on a flat, 1-dimensional surface such that she can only move either to the left or to the right. Now, this parrot is looking for a place to hide a treasure, so she wants to make a map. For this, the parrot chooses the place where she is standing as the origin, or the 0 position. The parrot decides that the treasure should be hidden somewhere close to where the origin is, so she decides to bury the treasure 3 steps forward from the origin. But what does forward mean? So she decides that forwards means towards the right of the screen. This is defined as the positive x direction. The opposite direction we shall call the negative x direction. Now that the parrot decides that the treasure should be buried towards the positive side, she looks around and cannot find a nearby landmark to reference the location of the treasure. So she decides to set a scale in steps. The procedure she uses is to draw some lines that are equally spaced, and each line represents the number of steps to the right from the origin. Since the parrot doesn't want to get confused, she defines the steps towards the left of the origin as negative, just as a reference. But the parrot wants to be clever. She wants to bury the treasure by giving directions. So she writes the instructions on the bottom of the map. Take 2 steps towards the left, and then 5 to the right, and dig. This is where the treasure is hidden. Of course, animations are very useful and can illustrate the process nicely. But what if we want to work in a more formal framework? Defining the coordinate system is a great first step. And we shall define the x-axis as the horizontal axis that has its origin at the mark labeled by 0. The scale is set by lines that are separated by the same distance and represent equally spaced values of x. In this example, each mark represents a single unit. Units towards the right of the origin are defined as positive units and appear in increasing order, and only a few units are shown, as x continues on forever. In a similar way, units towards the left of the origin are defined as negative units and appear in decreasing order, and only a few units are shown because, as before, x continues on forever. Now that we have defined the coordinate system, let's see the procedure in terms of vectors. Let's start by setting our coordinate system. Notice that we have defined the positive x side towards the right of the screen and the negative side towards the left of the screen. This is the standard system that is most commonly used, although it won't matter very much when you learn to use the vector symbolically. The instructions to get to the treasure are pretty simple. If we define 1 as the unit, the instructions are: move 2 units to the left and move 5 units to the right. So what you have just done is the addition of 2 vectors in 1 dimension. So let's define vectors in a more formal way. A vector is an ordered list of numbers that represents the number of units in a specific direction. You can define vectors as vectors of the different kind of numbers we have already learned. Of course, depending on the type of numbers, there will be allowed and forbidden operations. And we are going to be working with real numbers, so there is no ambiguity when using the vectors and operating on them. So to define a vector algebraically, we use a letter with a small arrow on top of it. A vector represented by the letter B is given by a B with a small arrow on top of it. In our case, the 2 vectors in this case are given by B1 equals -2 and B2 equals 5. Notice that the numbers are surrounded by parentheses. These parentheses hold the list of numbers that represent the units in the specific direction the vector points to. Adding 2 one-dimensional vectors is easy. You just add the numbers, making sure to keep the parenthesis that indicates that the sum of 2 vectors is, of course, a vector. Let's go back somewhat and see how vectors are added graphically. Define the coordinate system with the scale and origin defined. Draw the arrow representing the first vector from the origin to -2. That is how we define this vector, ending in the arrowhead. To add the second vector to the first one, draw an arrow starting from the arrowhead of the first one and spanning the number of required units in the required direction, ending in an arrowhead. In this case, 5 units to the right. The resultant vector is the arrow connecting the origin and the arrowhead of the second vector, as shown. So, using the arrow representation, we can infer some useful properties. The first property we can infer about is that of the length of a vector. We can see that the length of a vector in 1 dimension, that is also called the magnitude of a vector, is the absolute value of the number inside the vector. The absolute value for a real number is defined in terms of the quantity itself. Suppose we take the absolute value of a number alpha, and if alpha is a positive value, then the absolute value of alpha is itself. On the other hand, if alpha is negative, the absolute value of alpha is the negative value of itself. So, for example, the magnitude of the vector v1 is 2, and the magnitude of v2 is 5. We can infer how to multiply vectors by a scalar quantity. If we have a vector v3 that has length of 2, and we multiply the vector by 1.5, the vector will increase its length by 1.5 in the direction the vector is pointing towards. If the number had been negative, it would have reversed the arrow. So we conclude that when multiplying the vector by a scalar, it is just a matter of multiplying the number in parentheses. Using the previous 2 properties, we can now define a very important kind of vector, that is the unit vector. A unit vector is a vector of length 1. In this case, we define the unit vector pointing along the positive x direction as an eye with a small hat. So whenever a hat is used over a vector, it usually means that the vector has a length of 1. Notice also that any vector in 1 dimension can be written in terms of the unit vector I hat. Of course, there is another unit vector, but notice that for one dimension, there are only two unit vectors. Another property is that non-zero vectors can be turned into unit vectors by dividing the vector by its magnitude. And this unit vector will point in the direction of the original vector, but will have unit length. And finally, there is also the zero vector. And the zero vector is the additive identity for vector algebra. If you add the zero vector to any vector to either side, it will not modify the vector. So one-dimensional vectors have been very useful in helping us elucidate some of the basic properties of vectors. However, vectors in one dimension are not really that useful to describe the world in which we live in, that is, three-dimensional. So we are now going to take a look at two-dimensional vectors. Of course, vectors in two dimensions are way more useful than vectors in one dimension, and actually it is in two dimensions where we can start defining more interesting operations that do not make a lot of sense in a single dimension. Be aware that it is not that most of these more interesting operations are not defined in a single dimension, but they are not as useful as they are in higher dimensions. So, to start working in two dimensions, we use a grid that has a horizontal and a vertical axis, and we define the horizontal axis as the x-axis and the vertical axis as the y-axis. And we set scales for this axis, as shown. In this case, we see that the vertical dashed lines represent the lines along which the value of x is constant and are integer units from the origin. This is also the case for the horizontal lines, but these lines indicate constant values of y. So let's start by drawing the two-dimensional grid we had already defined. So let us now define what a vector in two dimensions looks like. And we should define a vector in two dimensions as a list of organized entries where the first entry represents the number of units from the origin in the x direction, and the second entry represents the number of units in the y direction, where we have defined x and y as real numbers. So let's explore the properties of a vector in a two-dimensional grid. Define a vector B as the arrow that connects the origin and the point 2, 2. And we can easily represent this by a horizontal arrow of 2 units in the x direction plus a vertical arrow in the y direction that yields a diagonal arrow. Now we want to get the length of the vector, and it is worth noticing that the horizontal and vertical arrows form a right-angled triangle, so we can use the Pythagorean Theorem to determine the length. That is given by 2 times the square root of 2. But now we want to multiply the vector by, say, -2. The procedure to multiply the vector by -2 is extremely simple. That is, you multiply each entry by -2. That yields a component of -4 in the horizontal direction and a component of -4 in the vertical direction. And when you draw a diagonal arrow, you get the graphical representation of the resulting vector. Of course, you can also get the length using the Pythagorean theorem. That is, of course, 2 times the length of the original vector, since we have increased the length of all the sides by 2. Notice that the length does not have to do with direction. You can flip or rotate any vector and preserve the length. In this case, we have rotated the vector by 180 degrees and doubled the length. So now the question is, how do we add two vectors? So let's define vector 1 as the vector 1 unit on the x-axis and 2 on the y-axis. In a similar way, we define the second vector as 3 units in the x-axis and -1 unit in the y-axis. So let's now look at the algorithm to add these two vectors. The first step is to set the sum to whatever it is. The second step is to replace the vectors by their list forms. And finally, add the matching entries. It is also important to know how to do this graphically. So the first step is to draw the first vector, represented by an arrow, starting from the origin and ending in an arrowhead. The second step is to draw the second vector, again represented by an arrow, from the arrowhead of the first vector with the respective number of units in each direction. And the final step to determine the resulting vector is to draw a vector from the origin to the arrowhead of the second vector, and this is the resulting vector. Of course, this procedure can be used to add 3 or more vectors. How about vectors in more than 2 dimensions? If you find it more comfortable to add vectors graphically, you will be upset to find that drawing vectors in 3 dimensions can be extremely difficult, and if you go to higher dimensions, well, it's impossible. But even if we cannot make explicit drawings, we can infer some properties. So let the first vector be a vector in n dimensions, where n is any positive non-zero integer number, and this vector has n slots where to place real numbers, represented by the double subscripted b's, where these slots represent the directions, as we have already seen with the vectors in 1 and 2 dimensions. In an analogous way, we define a second vector just for the purpose of performing operations with 2 different vectors. So the first property to be noted, and the most important, is that operations between 2 vectors have to be made between vectors of the same size. If the vectors are not the same size, no operations are properly defined between these 2 vectors. We are now going to assume that the size of the first vector is the same as that of the second vector. So to add 2 vectors, you write the sum, then you replace the vectors with their list forms, and to add the 2 vectors, you add the corresponding entries, as we have already done with the 1 and 2 dimensional vectors. To multiply a vector by a constant, you multiply each entry of the vector by the constant. Multiplying the sum of 2 vectors by a real number from either side is the same as multiplying each vector by the real number and then adding them. We also define the magnitude or length of a vector as the square root of the sum of its entries squared. And finally, let's introduce the unit vector. And we had already seen that the unit vector is a vector of length 1. For 1 dimension, there were only 2 unit vectors. However, for 2 or more dimensions, there are an infinite number of unit vectors. And every non-zero vector can be transformed into a unit vector by dividing it by its length. Other general properties of vectors include associativity. If we add to B1 the sum of B2 and B3, it is the same as first adding B1 and B2 and adding the result to B3. This allows us to remove the parentheses without any ambiguity. The sum of 2 vectors is commutative, so B1 plus B2 is the same as B2 plus B1. Vectors also obey linearity. That is a property we had already taken a look at, but it is worth mentioning it by using the proper name. So the properties I have mentioned are just the most common properties that you will encounter when taking a basic physics course. Now it is worth mentioning some other special operations with these vectors, and these operations you will use frequently. We will take a look at the dot product and the cross product. Of course, these 2 special operations are only a few of the special operations that can be performed with vectors, and I want to stress though that these other special operations are beyond the scope of this tutorial and require a more sophisticated treatment of vector and linear algebra. So let's take a look at the dot product. The dot product is defined in any number of dimensions as opposed to the cross product that is only defined in 3 dimensions. The dot product is an operation that can only be performed between 2 vectors, not on more than 2 vectors, not on less than 2 vectors, on exactly 2 vectors. The dot product turns 2 vectors into a scalar quantity. So define 2 vectors in n dimensions as we did a while ago. The dot product of 2 vectors is defined as the function that takes 2 vectors and turns them into a scalar quantity. As an abbreviation of the function, we use the dot operator between the 2 vectors, hence dot product. The way to take the dot product is to write the 2 vectors in this form side by side with a dot in between them, indicating that you are performing the dot operation. Once this is done, you multiply the first entry of the first vector by the first entry of the second vector and add the multiplication of the second entry of the first vector by the second entry of the second vector, and so on until you get to the last entry. And this will give you the dot product between the 2 vectors. Important, do not confuse the dot operator with multiplication by a scalar that sometimes is represented by the same symbol. So let's now take a look at how to take the dot product of two vectors in 3 dimensions. So assume that you have two vectors. Vector 1 is defined as -1 unit in the x direction, 2 units in the y direction, and 7 units in the z direction. In an analogous way, we define the second vector as shown. So we now want to take the dot product of b1 and b2. The first step is to write the dot product in list form. The second step is to multiply the first entry of vector 1 by the first entry of vector 2 and add the second entry of vector 1 multiplied by the second entry of vector 2, and finally add the third entry of vector 1 multiplied by the third entry of vector 2. And after adding the entries, you see that we get a number that in this case is 57, concluding that the result of the dot product between b1 and b2 is, well, 57. So let's now take a look at some properties of the dot product. The first property we encounter on the dot product is that it is commutative. So taking the dot product of b1 and b2 is the same as taking the dot product between b2 and b1. It is also important to notice that the magnitude of a vector can be defined in terms of the dot product as the square root of the vector with itself. We now define the two basic unit vectors in 2 dimensions. Let's define the basic unit vector along the x direction as I hat and is given by 1, 0, and the basic unit vector in the y direction is defined as j hat and is given by 0, 1. It is worth noticing that these vectors are perpendicular. That is, when drawn, they form a right angle with each other. It is important to notice that we can use the properties of vectors to write any vector in terms of the unit vectors, and this is very convenient since the dot product between these two unit vectors is 0. Now we say that if the dot product between two non-zero vectors is 0, the vectors are orthogonal, or when drawn, they make an angle of 90 degrees with each other, or imagined in the case of more than 3 dimensions. So now assume that we have a vector represented by the green arrow, and this vector makes an angle theta with the x-axis, and this defines a right angle triangle. Thus, we can use trigonometric functions, sine and cosine, to express any vector. And we can define any vector b in terms of the magnitude of the vector and the sine and cosine of the angle the vector makes with the positive x-axis. So when you take the dot product of any vector with the unit vector I hat, this will give the magnitude of the vector times the cosine of the angle between the positive x-axis and the vector. And this takes us to the next important result. The dot product between two vectors can also be written as the multiplication of the magnitude of vectors times the cosine of the smallest angle between the two vectors. And it is important to consider that this is valid in any number of dimensions. Let's now summarize some of the properties of the dot product. The dot product is only defined between two vectors and yields a scalar quantity. So the triple dot product doesn't make any sense, since the dot product between two vectors yields a scalar. So trying to take a third dot product doesn't make any sense. Of course, the sum of the dot product of two vectors with another vector is not possible, since the sum of a vector and a scalar is not defined. The dot product is commutative, so the dot product between b1 and b2 is the same as taking the dot product between b2 and b1. The dot product obeys linearity. The dot product of a vector with the sum of vectors is the same as the sum of dot products between the vector and the vectors in the sum. The dot product respects rescaling. That is, the dot product of a vector with another vector multiplied by a scalar is the same as the multiplication by a scalar of the dot product between the two vectors. As was already stated, the dot product of two vectors is the same as multiplying the individual magnitudes of the two vectors and then multiplying them by the cosine of the smallest angle between the two of them. The dot product can be used to define the magnitude of a vector and is given by the square root of the dot product of the vector with itself. This is called the Euclidean magnitude of the vector. Of course, there are more things for which the dot product can be used, but this can be inferred from the properties of the dot product. We now move on to the cross product, and the cross product is only defined in 3 dimensions. Yes, the cross product can be extended to higher dimensions, but it is out of the scope of this tutorial. The cross product is defined between any number of vectors. The cross product takes 2 vectors and turns them into another vector. The cross product between these vectors is given by the following formula. And I will not give details of where this formula comes from, but from the definitions that will follow, you can get it yourself. Now, before moving on, let's define the basic unit vectors in 3 dimensions. As in 2 dimensions, we define the I hat and j hat vectors as the basic unit vectors along the x and y direction. And we have to add another basic vector along the z direction. Notice that if you try to write any of these vectors as a sum combination of the other 2 vectors, you will find that it is not possible. So we can make the statement that if you are in n dimensions and can find n non-zero vectors that satisfy this property, you say that you have found a basis for the n-dimensional space. Since the ij and k hat vectors satisfy these properties, they define a basis for the 3-dimensional space. The basis vectors we have chosen for the 1, 2, and 3-dimensional spaces make what is called the standard basis. But to not deviate so much from the topic, notice that any vector in the 3 dimensions can be written in terms of these unit vectors. Now, going back to the cross product, notice that the unit vectors satisfy j cross k is I, that is the same as minus k cross j. The other 2 properties can be easily obtained by using the procedure to get the cross product for the unit vectors. The important thing to notice from this is that the cross product of, for example, j and k yield vector I, that is perpendicular to both j and k. The other cross products also yield the same. So from this we can get the following property. If b1 and b2 are 2 3-dimensional non-zero vectors, the cross product will yield a third vector, b3, that is perpendicular to both b1 and b2, provided that b2 is not a multiple of b1. For example, take the 2 vectors b1 equals 2, 1, 0 and b2 as 1, 1, 0 and take the cross product. This yields the third vector b3 equals 0, 0, 1. And you can look at the procedure in detail yourself, but the important result is that b1 cross b2 yields the unit vector k. Just notice that the dot product of b3 with both b1 and b2 yields 0, and none of these vectors are non-zero. So our hypothesis is consistent. Even more, try to prove it algebraically for the general case. It is not that difficult. So let's now look at some of the properties of the cross product. Of course, all of the following properties can be easily proven, but I will just give the result. The cross product in general is neither commutative or associative. So when taking the cross product of 3 vectors, you must be careful which operation comes first. Also, you must be careful with the order, whether it is b1 cross b2 or b2 cross b1. However, it is true that reversing the order just flips the sign of the cross product. The cross product obeys linearity. That is, the cross product of a vector with the sum of 2 vectors is the sum of the cross products. It respects scaling. That is, the cross product of a vector with another vector multiplied by a constant is the constant times the cross product of the 2 vectors. As for the magnitude of the cross product, this yields something similar to that of the dot product, but it yields the magnitude of both vectors multiplied by the magnitude of the sign of the smallest angle between both vectors. It is also straightforward to prove that if 2 vectors differ by a multiplication of a constant or are parallel, their cross product is 0. Of course, I have not detailed the subtleties and more sophisticated applications of the cross product, but these are the basic operations and properties of the cross product that you should be aware of. So before concluding the video, I do want to mention 2 more important properties of the dot and cross product. The first property is the area of a parallelogram. If you define a vector b1 and a vector b2, you can define what is called a parallelogram by closing the shape as shown. Squares, rectangles, and rhombi are particular cases of parallelograms. So the area enclosed by the parallelogram defined by the vectors b1 and b2 is given by the magnitude of the cross product of the two vectors. And this might be unimportant at first sight, but it is extremely useful when working with vector calculus. Of course, I will not go into vector calculus, but it is extremely important to define this. Even more, in vector calculus, you define the area as a vector, something that I will not comment more on. The second property is the volume of a parallelepiped. That is a difficult word to pronounce. If you have three vectors, b1, b2, and b3, the volume that these vectors enclose, as shown, is given by the cross product of two of these vectors and then taking the dot product with the remaining vector. Notice that it doesn't matter which vectors you choose for the cross product. Of course, if two of these vectors are parallel or the three vectors are in the same plane, the volume is 0. That is completely consistent with the definition of volume. And this is called the scalar triple product, and it is extremely useful in multivariate calculus. That is more complicated than the version of single variable calculus. So with this, I finished the mathematical part of this tutorial. And to summarize, we have defined vectors as organized lists of real numbers, where each entry refers to the number of units in a specific direction. We have seen that operations between two vectors are only defined if both vectors have the same dimension. For any number of dimensions, we have defined the multiplication of a vector by a scalar. We have defined addition of two or more vectors, symbolically and graphically, and the multiplication of the sum of two or more vectors by a scalar. Based on the entries of the vector, we have also defined the length of a vector, or magnitude, so that non-zero vectors can be made into unit vectors, or vectors of magnitude 1, by dividing the vector by its magnitude. Also, you can always write any vector in terms of the standard basis vectors, or any other basis that you can think of, or find, for that matter. Even more, for an n-dimensional space, you need exactly n vectors that can generate any other vector in that same dimension. So we have also defined the dot product of two vectors and the properties of the dot product. In particular, I want to stress that the dot product yields a scalar, not a vector. It is important to notice that the order of the operations matter when multiple vectors are involved in operations where the dot product is involved, so that they are done consistently. If the dot product of two non-zero vectors yields 0, then the vectors are said to be perpendicular. In fact, you can get the cosine of the smallest angle between the two vectors by taking the dot product of these vectors and dividing the result by the magnitude of both vectors, where both vectors are non-zero, and I want that to be clear. We have also taken a brief view at the cross product. The cross product is only defined in 3 dimensions and is the first case where we find an operation that is not associative or commutative. So again, order matters. The cross product between two non-zero vectors yields a vector that is perpendicular to these first two vectors. Also, in an analogous way to the dot product, the magnitude of the cross product is related to the sign of the smallest angle between the vectors. Finally, we took a look at 2 important geometric interpretations of these operations, where the magnitude of the cross product is the area enclosed by the parallelogram defined by the two vectors. The cross product is being taken on. Also, and this is to wrap it up, the volume of a parallelepiped defined by 3 vectors is given by the magnitude of the scalar triple product, that is the dot product of one of these vectors with the cross product of the other 2. Whichever, it doesn't matter. The next part of this video is optional, but it is useful to learn somewhat about plotting. So if you enjoyed and learned from this last tutorial in the series, please give the video a like and subscribe to get notifications for when more tutorial series come out. Just so that you are aware of, as of right now, I am creating tutorials in physics and hope to be releasing them as soon as I get them ready. So I guess, hope to see you soon. Bye-bye. Now that the math tutorial is over, I just want to quickly go over plotting in 2 dimensions since it is useful. Plotting in 3 dimensions is somewhat more complicated and requires much more intuition than plotting in 2 dimensions, so I will not go into it. I will be using the matplotlib package using Python 3.6, along with the pyplot edition, NumPy, and optionally the OS package. I suggest that you also install the SciPy package that contains a couple more tools that you might want to use, but it is not compulsory. So if you have not done so, please install these programs and modules before starting. I will not really go into how to install Python and the modules since there are plenty of online tutorials, and it is not really the purpose of this part of the tutorial to show you how to install any of these features. Please do look at the installation tutorials for the packages before attempting installation, since configuring pip for Windows can be somewhat difficult. For Mac and Linux systems, it is pretty straightforward though, so there's no problem with that. Now, just so that you don't miss the links in this screen and in the video description, I will provide the links to the videos on how to install Python 3.6 and the packages that will be needed. So again, before starting, and if you have not installed Python 3.6, install it along with the packages I just mentioned. Again, just be warned that this plotting tutorial is very brief and is meant to introduce pyplot as a tool for plotting, so don't be disappointed if it is not too long. So I have already installed Python 3.6 and installed the needed packages, OS, NumPy, and matplotlib. And to show you how to plot, I will use the editor that comes with the Python installation, IDLE. Of course, you can use any text editor and then compile the code. But I find that IDLE is a fairly good editor and it just serves our purpose. So the first step is to open IDLE, and since I'm using Windows 10, I can go to Cortana's search box and type IDLE and left click on the icon to open it. Now, IDLE is a console type program, so you type things into the console, and when you press enter, you send a command and the instruction is immediately executed. Now, this is nice, but it is not very useful when you want to input a long script and have to modify a lot of things if something goes wrong. So the best strategy is to save the commands to a file and then run the program in a single go. To do this, we will proceed to the File menu and click on the New File option. In this new window, go to the File menu and click on the Save As option. Once you get directed to the save screen, choose a folder where to save the file. I will choose the desktop as the folder where to save the file and we'll name it Test. Notice that if you go to your desktop, let me move this window a little bit, you will find a file named Test with the Python logo. This is mostly unimportant, and it is the standard procedure to open and save a new text file where you will write your script or program. So let's try and make a very basic plot. Let's start by typing the following: import OS, import NumPy as MP, and import matplotlib.pyplot as PLT. And you actually don't need the OS package, but it is comfortable to use it if you want to save the plot. Now, the OS package is used to get the file separator character, since getting the proper syntax to specify the path for Windows can be tricky. The other packages, NumPy and matplotlib.pyplot, are the ones that have the functions that will help us plot the graphs. Notice that I have used the term as, so we can call NumPy or the pyplot module, and we can abbreviate them as MP and PLT respectively. So let's now proceed to define a function of x. Say the equation of a line f of x equals x plus 2, and for this we type def func of x colon return x plus 2. So now that we have defined the function, we can plot something simple. I will show you how to properly plot a graph in this version of pyplot, since it has changed since the last version and the old way will soon be useless. Let's first get the image that is produced and the axis where we will plot. So the figure is named fig and the axis we'll name x, and is defined as PLT subplots 1, 1, sorry, where fig is the object that contains the image and x is the object that contains the properties of the plot. The two ones in parentheses, like these guys, means that there is a single pair of axes. This means that there will be only a single plot in the image, and we will see that in a while. So to begin, let's set the range. For this, we'll define two variables, xmin and xmax. That take values minus 3.0 and 3 respectively. So we must now decide how many points we want to use to generate the plot. And this is where plotting in pyplot becomes an intuitive process. And so what pyplot does under the hood is that it takes the points and joins them with straight lines. So if the graph is that of a straight line, there is no problem. The problem really comes when plotting nonlinear graphs, where the graph, have sharp curves. So 2 points are certainly not enough to properly represent the curve. And then the question becomes, how many points should I use to represent this curve so that it looks smooth? Of course, if you choose 1 million points, the curve is going to be really smooth, but you will need a lot of computer memory to plot this. So if you choose too few points, well, the graph is not going to look too good. And the answer is, it is difficult to tell. The sense of how many points have to be used to properly represent a smooth curve can only be achieved with practice. And in this example, since we are plotting a line, we can choose a few number of points. So let's choose 20 equally spaced points as our sample to generate the graph. Of course, 2 points would be enough, but just to give an example, we will use 20 points. So for this, we define a variable that contains the number of steps. In our case, I'm going to choose n steps equals 20, so that we can define a uniform interval of length step by step equals xmax minus xmin divided by the number of steps. So the next step is to get the x coordinates in the form of a NumPy array. And this is convenient since the NumPy arrays can be easily manipulated. I will not go into details, but the way that you define the coordinates is the following. So you say xcrds, that will be our x coordinates, will be a NumPy array, NP array, and then we define the usual array for a Python array. So a for a in NP arrange, that allows us to choose non-integer numbers, xmin, xmax plus step. Remember that the upper limit is not included, so we must choose an extra point, that is xmax plus step, in step intervals. And I will just define this as an NP double number. And to get the y coordinates, we can use the simple command ycrds equals func of x as passing the x coordinates as parameters. And this will give us the y coordinates as another NumPy array. So to plot the function, you can use the plot command on the axis x as we have named it. So x dot plot, first slot contains the x coordinates, second slot contains the y coordinates. Now to actually show the plot after the script has run, you must type the command plt dot show. If you do not include this last statement, the plot will not show. To run the script, press F5 or go to the Run tab and choose the Run module option. If the script is properly written, a window with a plot should show. It may take a while to open, so don't be impatient if it takes a while. Just make sure that you write the program as I have shown. Otherwise, the script might not execute properly or even not at all. So to save the plot, you can use the save icon at the bottom of the window. Just click it. Otherwise, you can type the command before the plt show as plt dot tight layout, and then under it you can save fig actually, plus os.sap plus test PNG to save the graph in PNG format, and this will save the image to the folder where the script is currently in. The use of os.sap is suggested since it will choose the appropriate separator depending on your operating system. The plot tight layout command just indicates that the box drawn around the plot is adjusted as close as possible to all the elements of the plot. Just to test it out, you can run the script again, press F5 and just save it again, and you will see that a small icon with the image appears here. You can double click. You can see that both images are the same. And of course you can play around with the script and the parameters of the script that I highly encourage you to do. And for a more advanced tutorial, you can look for more online videos, but this will at least get you started on how to make a quick basic plot. So thank you very much, and well, see you in the next video or some other video. Bye bye.